GM, everybody. Happy Wednesday morning. I'm Ellis. I'm the founder of Crack Labs, and we are super excited to have Sam joining us this morning to talk all things Somnia and really dive deep into the stack. Sam, say what's up.
Hey guys, nice to meet you. Thank you for having me.
So we're going to be keeping it pretty quick today. If there are questions as Sam is going through the presentation, be sure to drop them into the chat. We'll go back at the end of the presentation and do Q&A for a little bit. If, again, there are things that come up, let us know. But with that, I'm going to just hand it over to you, Sam. Take it away.
All right, brilliant. Yeah, so nice to meet you all. I'm Sam. I work on the team that builds Somnia, that builds the blockchain node itself. And today I'm going to be going through some of the major differences that we've built into Somnia that manage to lift the performance of an EVM chain as high as we have. So that's what I'm going to be talking about today.
Awesome. And let me know when you need the slides up there, and I'll just bring them up.
Okay, yeah. So yeah, I've got the slides here.
Perfect. 4 key bottlenecks to high performance.
Yes, that's right. So yeah, today I'm going to be talking about 4 key areas that we had to innovate in to up the performance of Somnia. And these areas are, firstly, I'm going to talk about execution speed. So how do we execute EVM operations fast enough to hit the throughput that Somnia has been able to do? Then I'm going to talk about the database speed. So, contracts don't just execute ops, they also store state and they read state. And this has been a big performance problem for blockchains up until now. And we've done a lot of work on our database to increase the performance of those reads and those writes. I'm then going to talk about bandwidth and explain who that man is. So this is the challenge of actually sending this amount of data, this amount of transactions across the world. All our validators are all around the world. And we had to do a lot of work here to make that efficient enough to be able to transmit over the internet. And then finally, I'm going to talk about signature speed. Each transaction has a signature, and that proves that the user has approved of that kind of piece of logic. And verifying those signatures is a big performance problem that I'm going to be talking about as well. And this is a really important point. None of these are valuable unless you solve all of them. And that's because your performance is only as high as your smallest bottleneck. Okay, so we could optimize execution speed by 1000x, database speed, bandwidth by 1000x, but if we don't have that signature speed, it's all pointless. And that's the same for any one of these bottlenecks. And this is a really interesting property when you're kind of trying to really move the needle. You have to solve all of these problems at the same time. Okay, great. So yeah, let's start with execution speed. So this is the kind of speed at which we can process the operations that your smart contracts do. So whether that's adding 2 numbers or dividing numbers or moving some memory around, these are all called ops. These are EVM ops, and we have to allow Somnia to execute those ops far faster than any other EVM chain on the market. So how do we do that? Well, you might know that a lot of projects are doing what they call parallel execution. So what that means is they say, well, let's take all the transactions that we have in a block. Let's work out which ones are related, okay? Which ones change the same pieces of state. And what they're saying is, well, a lot of the time, a lot of transactions in that block don't modify the same piece of state. They're not related in any way. And so what they can do is they run those transactions on separate threads, okay, separate cores of your machine. And this allows them to scale the execution, but only if those transactions are unrelated. So this is what we call an average case optimization, because most of the time during the day, transactions are unrelated. So this works most of the time, okay? But that's a really big problem because you don't care about your average case optimization. When it comes to throughput, you need to care about your worst case. Okay, the average case doesn't matter. It doesn't matter how good or how fast you are in your average case, because you need to build for the worst case still working. Okay, now the unfortunate reality of this optimization is that when you really need that performance is when you have a really high load spike. And when you have a high load spike, that means there's a correlation of activity in those transactions, and those transactions basically become very related. And what that does is it breaks down this optimization, because all of those transactions in your load spike, they're modifying the same state and they cannot be parallelized. So this is a really big problem with that, in our opinion. It breaks down exactly when you need it. So, for example, you might have a big NFT mint. The other side mint, I believe, was a huge, I don't know if it still is, but it was the biggest kind of gas price spike in Ethereum at the time. All of those transactions were touching the same state. Okay, so this optimization wouldn't have worked. Or to take kind of on a DEX, on an exchange, when you have high volatility of an asset, that's when you get a lot of transactions onto that DEX. But all of those transactions are changing the same state. So this performance optimization breaks down. So what we do instead is we say, well, let's not move things onto different threads. Let's not parallelize. Let's just make one single core go really, really fast. Okay, and this is crucially very different from the approaches the other projects are taking. We just make one core go very, very fast. And this means that even if all of those transactions are touching the exact same state, there's no performance degradation, because we're not assuming or relying on these transactions being different, like being independent. So how have we done this? Well, there's a lot of techniques to this. A couple of which are kind of turning bytecode into native assembly. So we've built two compilers, and that basically turns EVM code into instructions that your hardware, your CPU itself understands. But there's a lot more to that that I won't go into today, but that's what we do. Now, why is this a good thing? Well, your CPU kind of natively understanding it makes it go fast in of itself. But it also allows us to use what's called out-of-order execution. So your CPU, the kind of device that sits in your phone or your computer, I don't know if anyone's seen, like, well, I don't have a slide here, but you know, in the Matrix, when all the assembly and all those characters kind of come down the screen, that's what a CPU is reading, and it reads it line by line. So it says add two numbers, minus two numbers, do a conditional. It's got these instructions one after the other. But under the hood, inside your CPU, inside the actual hardware, it's got all sorts of things happening in completely different orders and at exactly the same time. Okay, so they're these really complex beasts, but typical code will only kind of like can't make use of that because of the way it's written. And what we've done is we've built these compilers in order to harness this out-of-order execution. And what that means is that your CPU is actually running lots of different logic of your smart contract at exactly the same time, but inside one core. Okay, and this speeds up every single transaction, not just transactions that are independent. All right, so that's the execution speed. What about the database speed? Yeah, it's all good having your operations run infinitely fast, but you've still got to do reads and writes. Every transaction does. And that's traditionally been a really big problem for blockchain performance. So what is the key problem? Well, unfortunately, databases, they store data in so many different areas on your computer. And each of those areas has a massively different latency. So what that means is you might read one key and it takes 100 nanoseconds. That's a tiny amount of time. But you might read another key, and just depending on where it happens to live, it might take 10,000 times that. Okay, so it's really unpredictable when you make a read. How long is it going to take? But I don't know if anyone here has seen kind of the S-load operation. So this is the instruction which your smart contract uses to read data. It needs to charge an amount of gas, and it needs to charge an amount of gas related to how long it takes to execute. So how much gas should you charge for this S load? Do you assume it's going to take 100 nanoseconds? Or do you assume it's going to take, a millisecond or even longer? And that's a big problem for blockchains. And what they typically do is they say, well, we can't assume the best case because then that's an easy attack vector. So we have to assume much closer to the worst case. And that's why reading state and writing state in a blockchain, or one of the reasons that reading and writing or modifying state is still so expensive. So what we've done is we've built a database called IceDB, and it has this property of deterministic performance. Okay, so that means that every single node, every single validator that's running Somnia is putting the data in exactly the same place on the machine. Okay, and that means that every validator will agree, at least approximately, on the time it takes to read a value. And what that means is we can actually charge gas based on what that read latency was. Okay, and we can do that because every node will agree on that fact, and therefore kind of the blockchain stays deterministic. Okay, so in Somnia, if you read or write or you modify kind of state that's been written in the last few weeks, it's really cheap, far cheaper than other chains. But if you're reading state that's really old and it hasn't been seen in a long time, that's when your database will put it over into the slower parts of your machine. Then we're able to charge more for that cost. Okay, so we're no longer assuming the worst case. We're actually charging you gas based on actually how long it takes to read from that database. And that's really important for scaling Somnia. Okay, who is this man? So I don't know if anyone here has seen that Somnia's testnet is called Shannon. Well, this is Shannon. So this is a man called Claude Shannon. And he came up with this theory a while ago that the bits you need to send information, the kind of bandwidth that you need to send information is related to the probability of that information. So if I flip a coin, its probability is a half that I get heads. And if you plug that into this formula, the bits you need for a coin flip for an even coin is 1 bit. Now, this is a really important formula, and it's kind of, we use this a lot when it comes to scaling the bandwidth on Somnia. And how do we use that? Well, actually, if you look at a transaction, there's a lot of redundant information. Okay, so each transaction includes the contract that is being called. And let's say there's a contract called by 10% of the transactions. Well, if we plug that into this formula, we get out the other end that address can be sent in 3.3 bits. Okay, that's a massive compression ratio over just sending it normally, which would be 20 bytes. So I don't even know what 20 times 8 is. I can't think of on the spot. But yeah, this is 50 times compression ratio over the uncompressed data. But this is a formula, and it's actually really hard. It's really difficult to get close to this theoretical limit in practice, and it requires a lot of work and a lot of re-architecting to get close to that limit. And that's what we've done with Somnia. So we utilize something called streaming compression, and I won't go into what that is here unless anyone asks us the question. But it's a different type of compression to what's typically used, called block compression. But to do this has a lot of restrictions. Streaming compression has a lot of restrictions. And what we've done is we've designed a consensus and dissemination architecture. So that's kind of how transactions are shared over the network in order to be able to use streaming compression. Okay, and finally signature speed. So yeah, as I mentioned, the fourth bottleneck we had to face was we can send all these transactions, we can execute them, we can read and write data really fast, but how do we up the signature speed? Well, I don't know if anyone here has heard of BLS signatures. So it's a different type of cryptography to elliptic curves, which is what Ethereum uses. And they have this really amazing property where you can take lots of different BLS signatures. So you know, everyone on this call could sign a particular message, and we can add them all up together into one number, and we can verify all of our signatures in the same cost as verifying one signature. So you could take all the transactions in a block and you can add them all up and verify it once, and that's the same as verifying all of our independent signatures, and that's really cool. But unfortunately, it requires us all to sign the same message, and we're not all going to want to do the same action on the blockchain. So we've basically built an optional transaction flow, which allows all of us to submit different transactions, but it has a protocol in which we all end up signing the same message. So what that does is it lets us all send our own transactions, but we can end up verifying just a single signature of that entire batch. Now that's really important, and that's one of the ways we can scale. But we've also more recently done a lot of work on optimizing the same signature scheme that Ethereum uses as well. So that's going to be getting released quite soon. It's called Husky, and it's basically kind of sat next to this is us taking the same signature scheme that Ethereum uses and upping the performance of that by multiple times. Okay, so yeah, this is kind of putting these together. Actually, this is a bit of an old slide. We've actually gone a lot higher than 400,000 now, where we've done tests over 1 million, which is really awesome. All at a sub-second finality, which is really important for real-time applications, all while allowing developers to use the EVM, which is really important for developer adoption. So we're really excited about how all of these properties can combine. And yeah, they can combine because of these 4 bottlenecks. So yeah, that's me done. Any questions?
Awesome. All right, let's go through the chat. Let's see here. Okay, guys, those of you in the chat, any questions for Sam about the speed, about any of the different unique features of Somnia? Somnia stream support for FPS gaming, sir?
Yeah, right. So I can talk about Somnia Stream. So Somnia Stream is a feature that we've been working on that allows, what I've talked about here is performance on-chain. So I've talked about how we up the throughput of on-chain logic. And that's great, but a lot of applications need to kind of read low latency data off chain, right? They need to be able to read what's happening on chain and get that onto the browser or the application or the app off chain. And likewise, a lot of applications need to write data on chain really quickly. This is shockingly hard. It's really difficult using Ethereum's APIs. It's really hard to get low latency data in and out of blockchains. And so what we're also working on is these features called Somnia Stream, which are basically a new set of RPCs, a new set of techniques that let your dApp read and write data at a very low latency from off-chain to on-chain, and then from on-chain back to off-chain. Will it support FPS gaming? That's exactly what it's built for. It's built for applications that need lower latency access, lower latency data than your typical DeFi applications. So yeah.
Awesome. Looks like there's, I don't know whether I'd call it a question, but it looks like there's some interest in exploring the deterministic features of the database and maybe how you guys came to that conclusion as a solution.
Yeah, of course. So I think there's two reasons we ended up building that. The first is we looked at the databases that other blockchains use. For example, a popular one that a lot of chains use is called RocksDB. And these are databases that are built for just general purpose applications. Okay, they're a Swiss Army knife of databases. They're amazing projects. They're really, really good, and they're pretty good at a lot of different things. Okay, but if you build a database for a specific domain, if you build a database for a specific use case, you can actually make very different decisions that can make it really good at one thing. Okay, and that's what we did with IceDB. So IceDB is really, really good for EVM state, but it's for other things that RocksDB is often used for writing logs, for doing all sorts of different things. It's completely the wrong choice. Okay, so we originally started building IceDB because we saw a lot of potential in building the database specifically for blockchain state rather than using a general purpose database. Okay, and then we were working on that. We found a lot of ways to up the performance really significantly for EVM state, such as like fixed size small keys and values. But we then came to, how do we cost it? You know, how do we charge gas for that when fundamentally a database will have such variance of its read performance, no matter what you do, because disks can be slow. And then that exercise led us to the conclusion that we need to charge gas based on where the data is in the database. And then that led us to the conclusion that we therefore needed to build a deterministic database. So that's the story of how we got there.
I'm sitting here muted talking. Great. So, question. When most of these teams that are participating in Dreamathon are post MVP, in some cases pre-seed, seed stage, fleshed out real teams, what should they expect to run into, or what types of things should they anticipate as they're going through the Somnia stack and as they're doing their integration?
Yeah, so kind of as a developer, what would they hit? I think a couple things there. So the first one is, you know, the cost of transactions and the cost of gas on Somnia and the latency and performance that you can get is very, very different to other chains, right? And I think a lot of developers face decisions when they're building dApps on other chains that, well, this state needs to live off chain. This state is important to be on chain, and it's low frequency enough, low throughput enough that I can put it on chain. I would, when you're building on Somnia, just rethink that. You know, rethink what stuff actually has to be off chain in a world where you have a really high performance blockchain. My hypothesis is you could put a lot of the state that you'd typically be putting in Superbase or other data, you know, off-chain databases. You can actually just build a lot more of that on-chain and simplify that split that you have to deal with. So I would encourage anyone to rethink that based on the, you know, significantly lower cost and higher performance of Somnia. I think the second thing, in terms of practically things that you might run into, you know, Ethereum has a certain gas model, so they've decided how much different operations charge. But because they're at such a low performance and they have so much breathing room, they are much less sensitive to if that model is good or bad, or if some things are cheaper than they should be or more expensive than they should be. And for Somnia and a lot of other high performance chains, they're a lot more sensitive to that, and so they have to be a lot more accurate with their gas model. And what that looks like is these chains, Somnia included, are making changes to that gas model. So when you run the same transaction on Somnia or the same transaction on Ethereum, the gas for each operation, for certain operations, will be different. And that's an important thing to keep in mind when you're developing or you're taking like a single transaction with a fixed hard-coded gas limit and moving it to a different chain. Now, our documentation like details all of those differences. As a piece of practical advice, I would say keep that in mind if you ever see an out of gas issue that you haven't seen before. That's likely the reason.
Awesome. Let me see here. I'm just going to pull this down. Okay. So it looks like there's not many questions coming out of the audience right now. Guys, if you are listening and you have questions about your personal integration that you're building out, let us know. Otherwise, great presentation, Sam. Sorry about that. I mean, I think that's pretty much it, man. So we can, at this point, sign off. If you can do me a favor and share those slides, we can get them uploaded into the Discord channel for everybody.
Yeah, of course.
And I assume you're also in the Discord for Dreamathon?
I am not yet. I need to join. I will do that.
There you go. So we're going to force you into the Discord. And for the builders that are listening, if you have questions for Sam, just shoot him a DM. And yeah, super excited to see what you guys were able to build. That is for sure.
All right. Cheers, everyone.
Sam, thanks again this morning. It's a pleasure. For the builders that are listening, again, get to work. We've got our first milestone due at the end of this week. If you have any questions, again, shoot us a DM. And everybody have an awesome day.
Thanks, everyone.
Thanks,
Bye.
Sam. Bye, guys.